The OSI model is a conceptual framework that explains networking or telecommunication systems as 7 levels, each with its own purpose. The OSI provides a standard for different computer systems to be able to communicate with each other. This model can be seen as a universal language for computer networking. What it basically does is splitting up a communication system into 7 abstract layers, each one stacked upon the last. Like one on top of the other, like when you played with your building blocks, or when you log on to your... Okay, you get it. But why does this model matter, and why does someone like you should know about it? You see, the world has evolved significantly in the last 20 years or so. The internet came, and the web turned up, and many things altered inside the web ecosystem. We started with simple HTML sites, then JavaScript, and now we have all these frameworks, which might be overlapping at times. Although the modern internet does not fully adhere to the OSI model, this model is still extremely useful for debugging network issues. Whether it's a single individual who can't connect their laptop to the internet or a website that's unavailable for thousands of users, the OSI model may assist in breaking down the issue and pinpointing the cause of the problem. A lot of unneeded work may be avoided if the problem can be focused on one single layer of the model. With that done, let's go over the OSI model. Number 7. This is what makes everything appear nice, and sadly, this is where so much of the glamour is, sometimes at the expense of everything else. Most software developers operate at the application layer. This is where your browsers live, but I'm not referring to software applications like Chrome, Skype, or Outlook. I'm referring to more fundamental things, such as protocols. For example, your browser makes a request to a web server using the HTTP protocol. Your email app uses the SMTP protocol to send and receive emails. You'd have to put 142.250.150.138 instead of google.com if the DNS protocol didn't exist. In a nutshell, the application layer is in charge of the foundation for practically all end-user applications. Layer 6. It handles 3 main functionalities. The first one is encryption and decryption. You don't want your data to be exposed to the world, which is why folks smarter than us devised Transport Layer Security, or TLS. It essentially encrypts your information and is also in charge of decrypting requests from other servers for consumption by the application layer. The second stage is serialization and deserialization. These are very big terms, yet they signify the same thing: translation. We want to translate our data into forms that our program understands. Simple data structures, for example, may be transformed into objects that our JavaScript program can understand. If we want our data to travel down the layer, we would translate our object into basic data structures that the lower levels might understand. The third stage is compression, and this one is a no-brainer even for someone like you. The fewer bits there are to send, the faster the request will be. This is also one of the presentation layer's primary duties. Keep in mind that this is a lossless compression, which means that no information is lost throughout the process. To be honest, most of these tasks are done in the application layer in the actual world. Layer 5. Sometimes you just have to reach out to someone. This is the layer that ensures you can communicate with anybody, everyone, someone out there, and that the world might actually be listening, or at least ready to take your money. The sessions layer's principal job is to handle client-server connections. But what exactly does that mean? Assume you wish to go to google.com. To do so, you must first connect to google.com. Thus you say, "Hey server, what's up? I want to connect to google.com." "Yeah, fine," the server says. Congratulations, you've now established a connection with Google server and can now make a GET request to get the page. To summarize, the layer is utilized for making connections, maintaining connections, closing connections. Number 4. This is where the action takes place. The transport layer is often specified by the protocol being used. The two most well-known are User Datagram Protocol, or UDP, and Transmission Control Protocol, TCP. TCP is a major protocol in the Internet suite. It is used on top of IP, or Internet Protocol, to ensure reliable packet transport. TCP resolves several IP-related difficulties, such as missing packets, out-of-order packets, duplicate packets, and corrupt packets. It is used in applications where all packets must be error-free, such as text messaging. UDP, on the other hand, is stateless, which means that it does not save any state between the client and server. It is also quite light, which makes it speedy. However, it is unreliable. Packets might go missing, become corrupted, and so forth. UDP is generally used when you don't mind losing a few packets here and there, such as while streaming video. Keep in mind that the data in this layer is referred to as segments. Now to summarize, TCP is trustworthy but slow, whereas UDP is unstable yet quick. Layer 3. This is the FedEx layer of the network. You know your item has to travel to Albania, but you have no idea how it gets there. But this layer figures it out, plans for it, and sends your package on its way. This is essentially the same as getting on an aircraft. You know where you're going, but you don't fly the damn thing and you're not communicating with traffic control. That is handled by the people who actually have a brain. It should be called the Internet layer since the Internet protocol is the most essential protocol here. The IP merely takes segments from the transport protocol and adds metadata to help identify where your client is in a local network. Message forwarding is another function of the network layer, which means it transmits your packets from network to network. Data in this layer is referred to as packets. Layer 2. Think of this as the post office. It takes your barely readable handwritten address, modifies it to make sense, and then passes it off, presumably certain that everyone else understands it. It can only provide it to something nearby, so it's like the regional postal code. Thankfully, it has Layer 3 FedEx to handle the long-distance things. The data link layer creates and ends a connection on a network between two physically linked nodes. It divides packets into frames and transmits them from source to destination. This layer is divided into two parts: Logic Link Control, or LLC, which identifies network protocols, does error checking, and synchronizes frames, and Media Access Control, or MAC, which connects devices and defines rights to transmit and receive data using MAC addresses. Layer 1. Physical layer. This is where Tron takes place. This is the Lego of today's world. Welcome to the core building pieces of everything that happens. Consider it the house's foundations, and like foundations, it has some cracks. Don't be misled by the term physical. We're not only talking about wires. Data, if you don't know, can be sent in a variety of ways, including radio waves and even light. Unfortunately, these modes of transit do not understand frames, just bits. This layer's role is to simply convert frames into bytes, or 8 bits, and transfer them over some transport mechanism, electricity, waves, light, and so on. Finally, our request will be sent to the server, and the server will repeat the procedure in reverse. And that is all you need to know about the OIS model and its layers. Fancy the video much? Then like and subscribe already. See you next time.